All right. So you've got the weekend to finish up your demand estimation. And remember that the elements of what you're submitting there are hand calculations, which are neat and logical and organized and well supported by reason and research. The summary table, and then a brief write-up that explains your rationale, your assumptions, the data that you used. So upload that by 1 o'clock on Monday, and then 1 o'clock on Friday of next week is the deadline for homework number 8, which I've just loaded onto Blackboard today. It's 10 questions where you're using Manning's equation. So you're going to get some more practice with trapezoidal channel geometry and solving for unknown flow depths, and you'll be an expert with Manning's equation by the end of homework number 8. So we're going to continue talking about some topics from Chapter 11, channel efficiency, resistance. We're going to talk about hydraulic scour today. Are there any questions about these announcements? Reminder about the Career Expo. Oh, Carrie, did you have a question?
Friday's the 10th.
Oh, thank you. Yeah, Friday the 10th. Good catch. And that's our last class meeting before spring break begins, right? All right. Good. Okay. Next Wednesday, the 8th, is the Career Expo. And so that's over at the Student Center from 3 to 6. I think there are well over 155 companies at this point. There's always a few who will join at the last minute. And I was looking over the list, and I think this is just some of the companies who are looking for engineers. There are a few others that I think are late additions that didn't make it to the Office of Career Education list for engineering employers. But there are going to be a lot of summer internship and co-op opportunities. It's a good chance for you to get to know some of the people who are anxious to hire young graduates. And so the Office of Career Education, of course, makes the suggestion that you dress up for the event, bring your resume, collect business cards, and so it's really a great opportunity, and I'll encourage you to attend. Any questions about the Career Expo? How many of you went over there in October of last year? It was, I thought, a pretty good event. It was a little crowded. You know, they may need to spread out a bit more if they get more companies, but I guess that's good. You know, there's a good energy in the room, lots of excitement. So I'd encourage you to participate in that. We didn't have something like this when I was a student, and the market wasn't quite as hot when I graduated. I think you're entering civil engineering at maybe the best time ever, just in terms of how much money is going into the profession and how many people are hiring and just a wide range of opportunity. We're really spoiled right now. All right, so this is a picture of a channel that has experienced quite a lot of scour. You can see that this is definitely not going to be considered a prismatic channel where it's not uniform. If we were to draw a line down the center of the channel, it's not a mirror image on the left and the right. Usually we like for that to be the case if it's an engineered channel, just for ease of maintenance, ease of operations. But in natural channels, there will become an equilibrium that depends on the strength of the soil or the rock combined with the slope and topography, and then also the amount of water that's going to be going through a channel and the stream power that it applies. And so in a situation like this, it would be very difficult for us to determine the flow depth using Manning's equation because it's so irregular. But we could break it up into little sections and apply Manning's equation across small elements, and we might be able to determine the flow depth that way. But the main thing I wanted to illustrate in this picture is just the idea that we can evaluate through geotechnical analysis the shear stress that a soil can bear and how much energy the water can be applying to the soil before erosion occurs. And so recall the shear stress formula here that says that if you know the unit weight of the fluid, So of course for water that would be 9810 newtons per meter cubed. And if you know the slope of the channel, which is unitless, it's units of rise, like meters of delta z, and then the distance between 2 points, so the downstream depth or downstream distance x. So slope is unitless, and now hydraulic radius is the last term in that expression. And so through geotechnical analysis, you can determine how much shear stress a soil or mixture of soils can bear before they start to be transported downstream. And the slope is usually a constant. That's just a function of the topography of the area. The water's going to be going from a watershed towards maybe a river or the ocean or another stream downstream. And so between those 2 points, there's a certain elevation drop, and so slope is fixed. So what we can do is we can calculate the hydraulic radius for a situation when we've got a combination of soil, slope, and the fluid being transported. Now that hydraulic radius in this first sense doesn't really have a physical significance, other than if you put it into the Manning's equation, you can calculate the velocity that corresponds to the shear stress that will cause scour. So the idea being that any velocity greater than the velocity you'd calculate in this way would cause a scour of the soil, meaning it's not going to be stable, it's not going to stay put, it's going to be moved and transported downstream. And any velocity less would lead to a stable channel. So you just substitute in rearranging this equation for R into Manning's equation, and you can solve for the maximum allowable velocity. So let's just put that into practice with this hypothetical here, that we've got a soil with a maximum permissible unit tractive force of 10 newtons per meter squared. So that's just how much shear stress it can bear before scour begins. So let's calculate in the case that we had a 1.5% slope, which is, that's pretty typical for watersheds in this area. By the time water is collecting together and is in a ditch or is in a stream, 1.5% would be pretty typical, not a large stream. I mean, the big rivers like the Ohio River, the Mud River, they have much shallower slopes than this. But a small creek that you might see in a rural area could feasibly have a slope of 1.5%. And we're going to assume that what we have in this channel is if we go to a Manning's N table, could be described as natural earth, a straight channel that's in good condition. So in a situation like that, it would suggest an N value of 0.02. All right, so we know the shear stress, we know the unit weight of the water, we know the slope, and remember that we should express the slope in terms of the decimal, so 0.01. So calculate the hydraulic radius, and then from this, determine the maximum velocity that can be tolerated. Okay, so the hydraulic radius that we've calculated here, 0.0680 meters. I guess one way to think about that is that would be the distance that we need to spread this shear stress out over when you've got a slope of 0.015. And so when we put that hydraulic radius into Manning's equation and solve for the velocity, it turns out 1.02 meters per second is the maximum tolerable velocity. And so in the homework assignment that I've just posted on Blackboard, you have a similar problem to this, where you simply calculate the hydraulic radius and find out how high can the velocity go and the soil remains stable. Okay, so any questions about this example? one of the topics that's introduced in Chapter 11 is the idea of velocity profiles. And you may recall from fluid mechanics the idea of the no-slip condition. And the no-slip condition says that when you have water in a channel and the water is flowing downstream, we could calculate the average velocity simply by having the flow rate Q divided by the cross-sectional area. That gives you the average velocity, but the velocity varies depending on how far away you are from the bottom of the stream. So for example, when you have the water that's just barely in contact with the bottom of the channel, the velocity is actually 0. And that's where the phrase the no-slip condition comes in, and that is that a fluid which has viscosity can't frictionlessly slip over a stationary surface. A fluid which has viscosity, meaning it's going to experience the effects of friction, will have a 0 velocity right at the boundary of a stationary object. But then the further away you get from that channel bottom, the velocity is increasing. So what we could do is we could say the further we get, the velocity is going up because there's less of the influence of the location at which the friction is applied. So this is a velocity profile, and here I've drawn it as linear. I guess more typically what we would do is we'd represent that with a shape that looks more like this, where the further away you get, beyond a certain threshold, there's diminishing returns where it's not increasing the velocity a lot more the further away you are. But the velocity at the surface of a stream is much higher than the average velocity. And so there are different ways that we can model and estimate what is the velocity at a certain depth when we know the average velocity, but we maybe need to identify, for example, if you throw a log on the top of a stream, it's going to be moving downstream at a faster velocity than something which is submerged and is flowing downstream. One of the ways that we can measure the velocity in a stream is with a device like this. You can see it has an impeller which is going to spin, and that's metered and connected to a calibrated sensor, and so that a certain number of rotations per minute is set to a water velocity. And so this could be dipped at a certain depth into the stream. You can see it's graduated here so that they know what the depth is that it's being put into the stream. And there's a lot of different formulas that suggest how you can translate the average velocity into a velocity at a certain depth. This equation is introduced in our text. It's maybe the most sophisticated or complicated way to approximate what the velocity at a certain depth, y, and here y is actually describing the distance upward from the bottom of the channel, where d is the total depth of flow. So, in this equation, the variables are a little bit different from most of the rest of the places that we are talking about open channels. Normally, we'd use the variable y just to mean how deep is the channel. But in this equation, which is introduced in the book, the channel depth would be d, the entire depth, and then y is some distance downward from the top of the flow. So what this formula says is if you know the average velocity, then you can find the velocity some distance downward by using the Van Karman constant here. It would depend on the depth of the channel, the slope, and then how far down you are. This equation is mostly good for estimating the velocity close to the surface. This equation isn't as good at estimating what is the velocity of the flow as you get closer and closer to the bottom of the channel. Then this formula gets worse and worse at predicting. And one illustration of that here in this figure, you can see that if you have a certain velocity as you're going downward from a flow depth of 2.5 meters, it actually would predict, as you get closer to the bottom, it would predict a negative flow velocity, which it doesn't happen. So the point is that you would use this equation to estimate the velocity in maybe the top half of a stream if you really needed to try and estimate how something floating at the surface would differ from the bulk average velocity. And so, like, some ways that could be, important is if you think about debris that floats at the surface during a flood, like logs and different kinds of trash that's flowing downstream in a flash flood. It can get hung up on bridges or in dam gates. And so if you have a quick flash flood and you're trying to estimate how long until some debris goes from one point to another, you couldn't simply just use the average velocity. You'd need to take the average velocity and then scale it up using an equation like this to know what's the velocity of the flow at the top of the stream. Or, if it's a relatively thick piece of debris, it wouldn't maybe be flowing at the top velocity. It would maybe be flowing at the, if you had a log that goes some distance downward, you'd need to find, the velocity at the average depth of the obstacle. So there are also simpler approaches for determining the relationship between velocity at a depth and the average velocity. If you're trying to figure out what is the average velocity, then you can use these equations to find the specific velocity at a certain depth. And so here the lowercase v is meaning the velocity at a depth of 40% of the channel depth. And so what this is saying is that oftentimes the average velocity is equal to the velocity at about 40% of the depth, or the average of 20% of the depth and 80% of the depth. Then you could get that to find the average velocity. So if you're using an instrument like this, you could take the meter about 20% of the way down and then 80% of the way down. And this is suggesting that the average of those two measurements would give you a pretty good estimate of the average velocity of flow in the stream. Because we take it for granted, in a lot of problems, I'll just tell you what is Q, the flow rate for a channel. But it's not very easy to measure the flow in open channel situations. If you have a channel, let's just say it's a trapezoidal channel, water's going down through like an irrigation ditch, for example. We don't immediately know what is the flow rate. Like, it's given in homework problems, but in the real world, you don't right off the bat know what is the flow in an open channel. You have to measure it. And so not only is the flow varying as you go down and up through the water column, but also the velocity is changing as you go left and right. Because the closer you get to the edge, the velocity will be decreasing, and when you're in the center, the velocity is higher. And so there are techniques where you'll break up a stream into segments, and you'd find out, what is the velocity in each of them, and then taking a weighted average to find the overall cross-sectional velocity, and then multiplying that by the area. This illustration is showing how sometimes we need to use a similar approach to come up with a weighted average n value. The roughness factor n that we use in Manning's equation, if you have a channel that's including a floodplain, can be very, very different for the combined n value than the n value of the main channel that ordinarily is conveying the flow. So, the channel that normally carries flow may be lined with concrete, or it could be grass lined, or in the side areas here may have riprap, which is broken up big blocks of concrete. But then in the floodplain, there can be all sorts of obstacles and debris which have a much higher n value. And so there's a variety of techniques, and probably the most frequently used is the Horton-Einstein method, which does a perimeter weighted average. And so you can see the formula here says that what you ought to do is for each of these different segments, which has different materials, like this edge of the floodplain maybe would have trees. This part of the floodplain maybe has a mixture of grass and stumps, or maybe some buildings or something. What you'd do is you'd find the length of each one of these sections, and you'd multiply it by the applicable n value, and then divide by the cumulative perimeter, and then take all of that to the 2/3 power, where we had taken the n value to the 3/2 power. So this weighted average then is an n value that you could use in Manning's equation for the cross section as a whole. So just to show you what sometimes these floodplains can look like, this is a drone video that I took a couple of years ago down at the Riverfront Park. So I'm sure this looks familiar if you've ever been to the park right by the downtown area. You can see there are picnic tables, garbage cans, signs, trees. You can't see, but it's submerged, is a bunch of shrubs and plants. And so, the water velocity is much slower through this section than in the center of the river. They had the flood wall up. You can kind of see that here. By the time I took this video, the water had receded to the point where it wasn't up against the flood wall. But I think maybe earlier in the day, the water level was even a bit higher. Okay, so to know the overall capacity of the Ohio River, you'd have to consider the elements individually. You'd need to know, how much water is being conveyed in this side floodplain compared to the main channel. And so what this weighted average method allows you to do is to calculate an n value based on the n value of each of the wetted perimeter segments. Okay, so Manning's equation. You remember that what we often do in Manning's equation is combine together the cross-sectional area that turns a velocity into a flow rate, which is this area, with the area which applies to the hydraulic radius. And so it's area to the 5/3 in the numerator, wetted perimeter to the 2/3 in the denominator. If we have a certain cross-sectional area that's fixed, and an n value that's constant, and a slope that isn't changing, because slope is just a function of geography. As a hydraulic designer, what we want to do is we want to maximize the carrying capacity of any channel. We want to have our channels be as efficient as possible. And at one extreme, if you have a channel that is very wide and shallow, I think you already have a sense that that wouldn't be efficient, because number one, it's very wide and you're going to have to pay a lot of real estate to buy all the land for a channel like that. But then the other issue of a very wide channel is that so much of the flow is right next to this wetted perimeter, which is exerting resistance. So it's not going to have a very high velocity if it's shallow like that. If we make the channel less wide but a little bit deeper, then this flow area, which is far away from the edges, is going to have a nice high velocity, and it will be able to convey more. So taking this as an illustration, and I think I hinted at this in one of the earlier class meetings, that if we have 10 by 2, that's not going to be the same flow rate as a 2 by 10. And the main reason for that is if we consider the wetted perimeter, it's different for each of them. So let's just put that to the test with Excel, just to look at, using Manning's equation, what would be the difference in flow capacity for these 4 different channels. So let me copy this into a new workbook here, and we're going to calculate the flow rate for those different channels. Okay, so if we're going to look at different B values, Y values, they'll all have the same area. They'll have different wetted perimeters and hydraulic radiuses. And then in the end, we want to know the flow rate using Manning's equation as our method of estimating the flow capacity there. So there is a 2 foot wide, a meter, 10 meter wide, a 5 meter wide, and a 4. We've got a depth of 10, 2, 4, and 5. And so the area will just be depth times width, since it's a rectangular channel in all of these cases. So all of them have 20 meter areas. Wetted perimeter, though, is going to be, in all of them, it's going to be the width plus 2 times the depth. Since it's rectangular, it is the bottom width, and then each side contributes to the wetted perimeter. So hydraulic radius is area divided by wetted perimeter. Okay, so we've got these different hydraulic radius, and now the flow rate. It's going to be the area to the 5/3 power multiplied by the slope. And I think in this illustration it's saying for a slope of 0.01 and an n value of 0.013. So I'll just hard key that in. The slope is 0.01, and that's to the power of 0.5. And now we're going to divide by the n value, 0.013, times the wetted perimeter to the power of 2/3. Okay, so this is going to be able to carry 144 cubic meters per second. Now what would be your guess for the next one? The one that's 2 by 10. Would you expect it's going to have a higher or a lower flow capacity? Higher. That's right. And why does it have a higher flow capacity? There's less wetted perimeter, and it's the wetted perimeter that is applying the shear stress that resists the flow. So less wetted perimeter, more conveyance. But we can do even a little bit better with these other ones. So you can see the 4 by 5 got us up to 205 cubic meters per second. But is that the ideal? Like, is that the optimal? Like, if we wanted to maximize, let's try something. I hadn't planned this, but I wonder if Solver's installed on here. I'm going to say it can change B and Y to maximize Q. Boy, it's been a long time since I optimized 2 variables at a time with Solver. Let's just give it a shot. Solver, okay. So in Solver, it's a little bit like goal seek, except for you can, instead of you have to know your target in goal seek, here I just want to maximize. So I want to maximize Q, and I'm going to tell it it can change both B and Y. I think this, hopefully this will work. Okay, solve. Oh, it needed a constraint. It just kept making it bigger and bigger. Of course, the constraint is that, remember, all of the areas have to equal 20. All right, so let me see. Subject to a constraint. Okay, so the constraint is that this has to equal 20. Okay. Now let's see what we get. Okay, this is interesting. It says that we could get 208.8 if we made it 6.32 meters wide and 3.16 meters deep. So let's keep that in mind in this next part, because there are these definitions of the most efficient cross-section. Like the cross-section that gives you the best Q for a certain cross-sectional area is the one that minimizes the wetted perimeter. And so back to our spreadsheet here, the wetted perimeter does in fact appear to be lower than any of the others, with this combination of 6.32 by 3.16. It minimized the wetted perimeter. And here's the parameters of the best trapezoidal channel. Let me come back to this because we're just dealing with a rectangular channel just now. So the most efficient rectangular channel is a half square. So a half square is the geometry where the area would be 2y squared, the wetted perimeter would be 4y, and the top width would be 2y. Okay, so here B, the top width, if we have a rectangular channel, the top and the bottom width are the same. So B and B are the same in a rectangular channel, and it's saying it should be the most efficient rectangular channel is 2 times y. 2 times y. Okay, so we've got some depth y, and it's saying that the width of the channel should be double your depth. Is that what we got in the spreadsheet here? The width of the channel is double the depth. Okay, so it all seems to hold up that the most efficient rectangular channel is the one that gave us the highest flow rate, same cross-sectional area as all the other ones, but for a certain depth, it should be twice as wide. And the reason why is that that is the shape that most closely approximates a circular cross-section. So like a half circle. So in the case of a triangular channel, then it should have an overall area of y squared. The top width B should be 2 times y because, for a certain depth, that would be the triangular geometry that approximates a half circle. So now back to the the trapezoidal channel geometry. Remember how we say T is a way to classify the side slope? The most efficient trapezoid is actually pretty steep side slopes, steeper than we could generally tolerate with a soil. Like soil would just kind of collapse in on itself if the T value is √3 divided by 3. So the square root of 3 divided by 3 is 0.577. So what that's saying is that the side slopes are 1 unit of vertical and 0.577 units of horizontal, gives you the most efficient flow. And it has other parameters here, for example, the bottom width, the resulting cross-sectional area, the total wetted perimeter, and so on for a given depth. So again, the trapezoid that is most efficient is the one that most closely approximates a half circle. And so it just coincidentally would have that T value of √3 divided by 3. So we'll do our best when we're designing channels to reduce the amount of area that has to be excavated, because digging soil and removing it from the ground costs money. So if you're having a certain flow coming out of a watershed and you need to create a channel to carry that flow, you're going to want to have the most efficient channel shape possible so that you reduce the expense of construction. So let's just put this to practice here by looking at the flow depth in the best triangular cross-section. If we have a flow rate of 2.5 cubic meters per second, N value of 0.013, and the slope of 0.01. I'll actually just show you the solution to this one because there's a different example I think is maybe more deserving of your time. So we want to find the flow depth for the best triangular channel like that. So that one, for the best triangle, we're going to have a flow rate of 2.5 cubic meters per second. And so we know Manning's equation here has area to the 5/3, and so for a triangle, the best triangle, the area, it says, is y squared. So you just substitute y squared into Manning's equation for the area, and the wetted perimeter for a best triangle is 2.83 times y. So we'll put that in place of the wetted perimeter down here in the denominator. We were given an n value and given channel slope, and so the only unknown here then would be the normal depth, and if you put it into your equation solver, then that suggests that the depth that you're going to experience for this best triangle is 0.851 meters. Okay, so what we did in this example, we just defined the area and the wetted perimeter in terms of the geometry that results in the most efficient conveyance, and it was in terms of an unknown depth, and that's what we ultimately solved for, was the unknown depth y. Okay, so that gives us now 8 minutes to look at this final example here. So this is just another instance of Manning's equation, unknown depth. So remember that if we substitute in the formula for area and wetted perimeter, this is what we're trying to solve. We've got a bottom width of 2 meters here, bed slope of 0.75%, so S will be 0.0075. 1-to-1 side slopes means that T is 1. And this is a grassy channel that has 0.035 n value. So we're just trying to solve for what is y in this trapezoidal channel. So I was circulating around and I saw several people had 2.03, but that's not what I get. I get 1.981. 1.819? Well, I got 1.981 meters, and I'll double check that because, I always want to be sure about it. But let's just look and make sure that we all agree about Manning's equation. So I just rearranged Manning's equation to put all of the constants on one side and the unknowns on the other. So we've got 21 cubic meters per second, the n value of 0.035, the slope in the denominator, the right-hand side. So the area is 2 plus y, since t is 1, times y, 5/3. And then the wetted perimeter 2 plus root 2 times y. So I think it should be 1.981. I'll double check that using Excel, and I'll email to let you know. All right, I'll email you the Excel and also this solution, because I think this is right, but boy, some people who I usually trust didn't get the same thing, so that makes me a little nervous. It makes me want to double check. All right. Have a good weekend. I'll see you on Monday. Remember, you've got that demand estimation, so I'll just be living by my cell phone all weekend long waiting for your emails and questions. So just let me know if I can help you. I'll be eager and happy to help.